Hey everyone, I am Sarthak Kamalkishor Dhole of 9th grade here with my video explaining the phenomena behind the ruler trick. The equipment that we have for this experiment is a 30 centimeter ruler that has its fulcrum about edge of the table, a A4 size for 70 GSM paper sheet, an eraser and a smiley ball, along with a glass filled with water and a lid for our next experiment. We know that the reason that this ruler is now balanced is because it is in rotational equilibrium and the net torque about its axis of rotation at this moment is 0. This portion of ruler, that is its free end, is known as the cantilever. We all know that when I drop this ball onto the edge of the ruler, it will rotate in a clockwise manner and then fall to the ground. Let us discuss why this happens. And this happens because as the ball strikes the cantilever, its velocity changes and so does its momentum. And we know from the very popular Newton's second law that a change in momentum causes for a force to act. This force then produces clockwise torque about its axis of rotation. We know that torque is just force times the perpendicular distance from its axis of rotation, which in this case is the edge of the table. So that is why it loses its rotational equilibrium and rotates and falls down to the ground. So if I cover this end of the ruler with a paper sheet, we can assume that it would still fall to the ground because the force acted upon by this ball onto the edge of the ruler would be greater than the weight of this paper sheet. But that is not what happens. It is not because of the weight of the paper sheet. We have another object that is more heavy than the paper, an eraser, and we can try it again, but it falls down to the ground. That means that the reason that the paper can withstand a change in its rotational equilibrium is not because of its weight. It is because in our surroundings we have air pressure all around. It is also beneath the paper there is air pressure at the moment, and this air pressure we can approximate to 1 atmosphere, that is just 1.01 by 10 to the power 5 Newton per meter square or pascals. But at the moment that the ball strikes the free end of the ruler, it lifts up the paper and it increases the volume below this paper, and the air below the paper tries to occupy as much volume as it can, thus dropping the pressure that exists below this sheet of paper. We also know this by Boyle's law or the ideal gas equation. Increase in volume causes the pressure to decrease, and we know by the laws of diffusion that the air in the surroundings that is at a comparatively higher pressure will try to move to the point that is at a lower pressure below the paper. But as we know that when the ball strikes the free end of the ruler, it is an impulsive force in nature and thus it is very short lived. Therefore, the air does not get enough time to move in and fill the void that exists below the sheet of paper and balance it. Therefore, it cannot equalize the pressure, and there exists a net downward pressure that acts on this sheet of paper. We know that force is just pressure times the area, and as the area of this paper is comparatively larger, there acts a very great amount of force onto this sheet of paper, which can even withstand a ball that drops onto that strike free end of the ruler, and it can balance its torque. The force that acts on this covered end of the ruler produces a torque that can counteract and resist clockwise torque of this ball. But if we do this same experiment at a slowly, if we push down the same mass but at a slower speed, we can see that the ruler will drop. This is because the air gets sufficient time in this case to move below the paper and it can equalize the pressure. Thus, the torque can produce an imbalance in its rotational equilibrium. Here is another experiment that shows the power of atmospheric pressure. It is a very common experiment with a glass of water and a lid. It might seem like magic, but it is not. It is only the power of air pressure that can withstand the weight of such a large water column. Thank you.